why are we taking these?
Sell it.
Okay, let's go. Oh! Oh! It's too heavy, man. Why don't we take something lighter? There's nothing else. Let's take one of them.
No.
We can make money off
Gentlemen, please have a seat so we can start today's lecture. As you all remember last week, we took our Schrodinger equation, this one up here, and we changed our Hamiltonians, as we can see in the back, so we could solve for the single particle and infinite potential well. Today we are going to find the... Yes.
We don't understand any of that.
You don't want me to lecture?
Well, I mean...
I can leave.
No, I think,
Do you mind?
no, this is, you're supposed to be here, but, maybe something about how to make a spectrograph.
Yeah,
Yeah.
spectrometry.
Yeah.
Is this Physics 541?
Hey, what class is this?
Wait a minute. Who are you guys?
We're
we're your helpers. Yeah.
helpers.
Very well then.
Yeah,
Well, if you guys
help.
are here to help me, let's get started. Today we're going to be talking about light. So visible light is electromagnetic radiation in the visible spectrum, so we can see it. Now there are many examples of different things that light do in this very room. As we can see, light is coming through the windows, meaning that a window is a transparent object. Does anyone have sunglasses? Those block out certain parts of it, so those are translucent. They only allow a few things. And then we have walls, which don't allow any light through them.
Professor,
Yes. Yes.
electromagical migration, what is...
Yes. Electromagnetic radiation, sir. It is a form of energy that can travel through space without the need of a transmission medium.
A transforming medium? What is the...
Oh, like cell phones and TV and radio.
Yes, exactly.
Yeah.
And like sound, like when I crank up my music real loud?
No, actually that's not correct. Sound needs a medium to travel, which is air. Without air, you wouldn't be able to hear anything, just like in space, even if your volume was turned all the way up.
What's a transmission medium? I don't understand.
Transmission medium is simply a material that allows for energy to travel through it. Like electricity travels through electrical conductors like wires, and sound travels through air. At any rate, here are some examples of common electromagnetic radiation. We have radio waves, we have microwaves, we have infrared waves, visible light, ultraviolet light, X-rays, and gamma rays. Each of these is classified by their frequency, or how fast they oscillate, go up and down, 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 up and down. The higher the frequency, the faster they oscillate, and the faster they oscillate, the more energy that they have.
Oh, so like if he is the radio waves and I'm the gamma rays,
Yes.
I like go super fast while he's really slow. So like this. Ready, go.
Actually, that's not the case at all. See, all electromagnetic radiation travels at the speed of light, which is about 670 million miles per hour. However, they do oscillate at different frequencies, meaning that the higher the frequency, the more energy they have while they're traveling.
Okay, so like this.
Yes, this time you got it right. Actually, the speed of the wave depends on the medium in which they are traveling. So when light travels through air, it is actually traveling a bit slower than 670 million miles per hour, but we just round up. Anyways, as I said earlier, the energy a wave carries increases with the frequency of the wave. So some of these are so powerful they can actually hurt living organisms, like you guys.
That's the sunlight, the ultraviolet. That's why we wear sunscreen, right?
Yes. Oh.
X-rays.
Oh, X-rays, yeah. You wear
Yeah.
the doctor and they have that big heavy. what is-
Apron.
Oh, but it's like you
Yes.
put it on. Like, ugh.
They put that over you to protect the parts of the body from the X-rays that the doctor doesn't want to see. Anyway, at any rate, visible light is actually the smallest part of the spectrum. If we graph the entire electromagnetic spectrum graphically, we see that visible light is only a small portion right in the middle. Now, all light is made up of these different colors, and each of these colors has a different frequency associated with it. Red light has the lowest frequency, where violet has the highest. And if you mix all these together, you actually make white light. Now, when a light wave is traveling in one medium and reaches a boundary with a different medium, say air to water, one or more of the following things will happen. The wave will be refracted, the wave will be reflected, or the wave will be absorbed.
Well, I've heard of reflected, but what's refraction?
Refraction is simply a change in the direction of the travel of a wave when it comes in contact with a boundary. See this incident light wave? If it had never met this boundary, it would have just kept going forever in that same direction. But once it hit the water, it bent and changed directions. So if you see this straw right here, you'd think it would keep going this way, but when you look at it, it goes that way because the light is bending.
So this dispersive, when it changes the frequencies and the light slows down, the colors, they can separate, right?
Yes, we see that in a rainbow. A rainbow is a natural example of a dispersion. Because the suspended moisture is a dispersive medium, the different colors travel at different speeds once it enters there and refract, and that's how we see all the colors.
Where are the colors coming from?
He told us that already. The white light has all the colors. Pay attention.
Speaking of paying attention, who's ready for a pop quiz? Alrighty. So we're going to say that we have white light, which is made up of all these frequencies traveling through water. Now, which color is going to be moving the fastest? And remember that the higher the frequency, the slower it's going to run. You right here, standing up.
Purple.
Not quite. It's because it's got a really high frequency. Remember, the high frequency
So it
is going to
should
drop.
be a red.
You are correct. Give her some candy.
Oh.
For you in the back there, because you seem so disappointed. Between the yellow and the green, which is traveling faster?
Yellow.
Give her some candy.
She got it right answer.
Back to the lecture. A wave is reflected when it changes the direction of travel at the boundary between two media. Has anyone ever looked in a mirror?
Yeah.
That's what's happening. The light is coming off of you and reflecting right back at you.
It's like another mirror and another mirror. Like once it from one mirror, and then it goes back.
Mm-hmm. So if you were to shine a light, say on a mirror, the reflected wave would have to reflect at the same angle. That's the law of refraction. The same thing happens with colors. So when you're looking at your red homework, what you're actually seeing is white light shining on your homework, and only the red light is reflecting off of it. That's how you see colors. The color white is actually not a color. It is a combination of all the colors of light. Conversely, an object appears white because it does not contain any pigments or any inks of any color. A white object is actually reflecting all the different colors. That's why you see it as white. The opposite is true of black. So black actually is not a color either. It is the absence of all light, or any colors of light. Conversely, an object appears black because it doesn't have any pigments or ink. Therefore, it's absorbing all the colors and appears black.
So,
Like in a car, whenever the sun comes, it doesn't like go off to the
Yep.
void. It stays.
Mhm.
so what you're saying is some pigment reflects light, and all light's electromagnetic radiation. You said that earlier. Does that mean some pigment can reflect other electromagnetic radiation?
Yes, absolutely. But we actually can't see these, so we've had to invent different types of instrumentation so that we can see these. So this is a fireman standing in a smoky room. Now he's not going to be able to see anything because of all the smoke. But if we move into the infrared spectrum,
I can't see.
we can actually see that there is somebody in the smoke laying on the floor. This is an extremely important technology in rescue operations for police and firemen and military. The same also happens in nature. So flowers naturally fluoresce, which means they emit frequencies above the visible spectrum in the ultraviolet. Now, if we were to see these flowers as bees see them, because they have special receptors to see, they can actually see the ultraviolet light being emitted where the pollen is. So it leads them right to the center of the flower.
Next year, it's like they have extra glasses on.
Some ways.
But isn't ultraviolet light the sunlight we said, and that's harmful, right?
Yes, ultraviolet light can be dangerous. Does anybody know what this symbol means?
Ooh,
Anybody?
I know.
Anybody?
Oh,
The guy standing up in his chair.
Yes.
He-
That means that those waveforms, like that light, is used by pirates.
Absolutely not. This symbol, these symbols mean that there is dangerous radiation present,
Which is dead.
which means your body could get very harmed or you could even die from it.
Dead.
Man, we're wasting our time here.
But, say, how would you know how to say make a spectroscope?
Yeah, the spectrum.
Yeah.
Yes, the movement of electrons inside of atoms produces electromagnetic radiation. Each element under the correct condition radiates a unique combination of these frequencies.
So, if we have a spectrograph, we can see these frequencies and know what element it is.
Yes, using the technology we talked about earlier, we can create an instrumentation to actually see the frequencies that are being emitted by these elements.
So where do you get it?
Where do you get what?
The spectromobility.
Oh. We're going to build one today. I have the instructions right here.
Oh, we'll help with this.
Wait,
Oh,
give those back.
we're helping.
Give those back. Bro, stop going through my stuff. That's my stuff. Stop going through my stuff. Wait, don't touch that. Don't touch that. Put that back. Get that.
Ta-da!
You made that?
Yes.
Well, there's the instructions.
Yeah. We
So,
followed.
this is the spectroscope, right?
Yes, absolutely.
Okay. Run!
Ah! Oh no, I need that back. Thank you guys for joining me for this lecture, and please join me next week when we talk about non-Newtonian fluids.